Hi, chemistry students. We're going to move on to the third section of Chapter 5 in discussion of atomic emission spectra. I'm wearing headphones today. They're really big, but I know that it will sound much clearer to you, especially as I write on the board and so forth. So anyway, moving on to atomic emission spectra, and I think you probably talked about this in 9th grade physical science, electromagnetic spectrum, visible light, and so forth. And so the reason this is called electromagnetic is because it has electrical waves, if you will, and then also magnetic waves. And so we say they are electromagnetic. And this includes, obviously, visible light is one really common component of that electromagnetic spectrum. But that's just a tiny, like we're looking at like, here is visible light, right? So it's an incredibly tiny part of the visible spectrum, or of the electromagnetic spectrum. And then there's lots of other things that fall onto this spectrum, like, I don't know if you can see this because it's not really big, but let me see if I can make this a little larger for you. There we go. So things like radio waves, both AM and FM radio waves, are actually on the electromagnetic spectrum. They have some, this is just for size reference. So the wavelength in meters, this is 10 to the third meters. So remember, a meter is just over 3 feet. So these are very long waves. And as we move across here, so radio waves are actually very long waves. FM radio waves are a little shorter, microwaves are a little shorter still, radar is shorter, and so on. And then as we move across here, so we have infrared, which we can't see. Some animals can see into the infrared and also ultraviolet spectrum, but we as humans can only see the visible spectrum. And then we have X-rays and some of the very shortest wavelengths that we know of are gamma rays, which we have lots of gamma rays in outer space. So today we're going to talk about, obviously, what the electromagnetic spectrum is, which we kind of did already, and then we're going to talk about some of those functions of how you can measure parts of that electromagnetic spectrum. Specifically, how we measure wavelength and frequency of those given waves. All right, so a quick review, and again, I'm pretty sure you've talked about this before in your high school career, but maybe it's been a couple years, so we're going to do a quick review of wave behavior and how we measure waves. So when we talk about wavelength, what exactly are we measuring? Well, wavelength can be measured actually several different ways, but we want to know the length of one wave. So we can either choose to measure, from what we call crest to crest. So the very top part of a wave is called a crest. The very lowest part of a wave is called a trough. And wavelength is either from the peak of a crest to the peak of the crest on the next wave, or we can measure trough to trough. It doesn't matter, as long as you're going from the same point on each wave. And so here I have it drawn on here as the wavelength from trough to trough. So we would measure this and meters is the accepted standard for measuring that. Even if they're very tiny, we use meters. Amplitude is the height of the wave, but it's the height of the wave from rest position. So not from trough to crest, but instead from rest position to crest. So what we're going to focus on here is how to determine wavelength and also frequency. So frequency is the number of waves that pass a given point per unit of time. And it's represented by, we just love Greek letters in science, so this is represented by, it looks like a V, but it's actually called nu. So, and nu is measured in waves per second. We also call that unit hertz. So hertz is just waves per second. So hertz, and if you look at your AM/FM radio dial, you will actually see that noted that AM radio stations, kilohertz, FM radio stations, megahertz, and if we want to actually do a comparison of frequency of different waves, let's do a quick example here. So I have two waves. I have a red wave and I have a blue, whoops, not sure what happened there, a blue wave. And when we talk about frequency, so all waves move at the same speed. They actually move at the speed of light. So I'll talk about that in just a moment. But so if both of these waves are moving at the same speed, you can see that there are going to be more waves per second that pass a given point with the blue wave. So we say this is a higher frequency wave, and the red wave is a lower frequency wave. So higher frequency wave, lower frequency wave. And again, I just mentioned, we talked about amplitude. All waves on the electromagnetic spectrum move at the speed of light, which is 3.0 times 10 to the 8th meters per second. If we expressed that as a whole number, $300 million meters per second. That's how fast all electromagnetic waves move. That's how fast light moves. That's how fast radio waves move. Anything that's on this electromagnetic spectrum, X-rays and so forth, radar waves, all of these move at 300 million meters per second. So because we know that, there's actually a formula that we can use. If we know the frequency, we can calculate wavelength. If we know the wavelength, we can calculate frequency, because again, the speed of light is always the same. So I'm missing wavelength times frequency. I must erase it. There we go. So that's my formula. So a couple of things. So this is our formula. Remember when we learned about density, I kind of gave you this little cheater wheel. So if I say C represents the speed of light, I have to multiply wavelength times frequency to get the speed of light, which is a constant. So obviously you're always going to have, you'll always know the speed of light. That's not one you're ever going to have to calculate. So, but if I take the speed of light divided by wavelength, it will give me the frequency. Or if I take the speed of light divided by frequency, it will give me the wavelength. So that's a pretty cool little visual or manipulative that we can use for solving for either wavelength or frequency. So let's do a quick problem here. So what is the wavelength of a wave with a frequency of 3.5 times 10 to the negative second hertz? So I already know what C is. I need to solve, in this particular one, I need to solve for wavelength. So I just need to take the speed of light divided by the frequency to get wavelength. So wavelength is equal to the speed of light divided by frequency. That's the way I'm going to use this manipulative or this equation. So if the wavelength, wavelength has a frequency of, so I'm just going to take 3.0 times 10 to the 8th meters per second divided by my frequency of 3.5 times 10 to the negative second, and this is, it's hertz, and you can just write hertz, but I know that this is cycles per second, so that seconds is going to cancel out. I also know that wavelength is in meters, but that's why it cancels out, just so you know. And then I'm just going to grab a calculator and do the math quick. And I just want to remind you, when we solve problems like this, we do want to put parentheses around this number. This is all one number written in scientific notation. This is all one number written in scientific notation. So put parentheses around that so that hopefully that makes sense. I mean, your calculator, if you just punch this in, it's not going to recognize it, and yeah, you just have to do that in order for it to know that this is a number, this is a whole number. And if I did my math correctly, this is 8.6 times 10 to the 9th meters for wavelength. You will notice that when I set this up, I just took the speed of light divided by that frequency that I was given, and that's literally how you're going to solve for everything except the speed of light, in which you would take wavelength times frequency. So let's do one more example. So let's analyze this problem really quickly. So what is the frequency of a wave with a wavelength of 7.0 times 10 to the 3rd meters? So I am given the wavelength and I'm solving for frequency. So remember, wavelength is this one. So I'm going to take the speed of light, although it wouldn't matter, speed of light divided by wavelength to get that frequency. So my formula is, let me pick a different color, the speed of light, which is c, divided by wavelength, is going to give me that frequency. So 3.0 times 10 to the 8th meters per second, that's a constant. That never changes. That's the speed of light. So again, just like the other one, I'm going to take the speed of light divided by whatever number I'm given. In this case, I'm given the wavelength, 7.0 times 10 to the 3rd meters. And again, I want to, I don't know why it's doing that today. I want to put parentheses around this so that my calculator knows that these are indeed like numbers that should be considered all together as one. I'm going to pause while I calculate really quick. All right, my handy dandy calculator. I have the answer. I'm going to round. It's 4.2857. Actually, I have to put this in scientific notation, but I'm going to round to 4.3 times 10 to the 1, 2, 3, 10, whoops, to the 4th, and this is frequency, so I'm just going to put hertz. I know that means cycles per second. So there you have it.